So, we have been discussing with gyrators and we were drawing it like that. These two are input port and these two are output port, and relationship of the input port voltage and currents are like this, and you can always write its Z parameters or ABCD parameters, but always be careful. I have been doing all these things with this direction of I 2. Z parameters will be absolutely fine, but ABCD parameters, when you do minus I 2 you replace by I 2, because of the fact for ABCD parameters only it is taken outside, flowing away. In case of transformer also, be careful while writing the ABCD parameters or Z parameters, because in Z parameters I 2 is assumed to enter into the circuit through the output port. Anyway, this is the thing, gyrator. Now, this gyrator people use a different symbol instead of drawing a box, so that you can easily identify it is a gyrator. It is drawn like this: a line, single line, two ports and a thing like this. This is how it is represented. Input port and this is V1, this is I1 and this is V2 and this is I2. This is how the gyrator ports, a gyrator is represented in this fashion. To distinguish it from other two port network, just looking at it, one indicates that it is a gyrator, then this relationship holds good. So, the relationships are then V 1 is equal to minus k into I 2 and V 2 is equal to k into I 1. This is the thing. We have got this. Now, that I have explained to you that how an inductor gets converted into a capacitor or capacitor connected at the secondary port will look like an inductor. These things we have done, but let us do it also mathematically just in one step, that this equation or this equation can be written as I 1 by V 2 by k from this equation. Then these two equations, if you divide V 1 by I 1, it will become equal to how much? Minus k square into I 2 by V 2. Acha. Suppose you have connected any impedance, need not be inductance or capacitance here. Suppose some impedance you have connected Z, complex impedance you have connected. Then, then this relation hold goods, because current entering. So, this is the thing. So, V 2 by Z, if I do, I will get minus I 2. I 2 is entering, V 2 is this voltage plus to minus. So, V 2 is equal to minus I 2 into Z, that is the thing. Therefore, V 2 by minus I 2 k square by V 2 divided by minus I 2 will be the thing, which is equal to k square by Z, whatever impedance you have connected. Therefore, Z in is equal to V 1 by I 1 is equal to k square by Z. K is what? K is the constant of the gyrator. If I know this value, then I find that the input impedance is some constant by Z. Mind you, you should not consider this to be admittance or things like that. This is the equivalent impedance in ohms seen by the source. For example, if Z happens to be 3 plus J 4 ohm in general, then Z in will be k square, which is a number only, by 3 plus J 4, which you know it is equal to k square by 5 angle some 62 degree, 53 degree or things like that. This is the impedance we have connected. So, this impedance value will be k square by 5 and minus 53 degree approximately. So, this is the thing. Now, what is this impedance? 3 plus J 4 was inductive impedance, R and L inductive impedance, but this one, if you break it up, this is capacitive impedance, this is capacitive RC, capacitive, that is RC impedance. Therefore, unlike transformer, it not only changes the magnitude of the impedance, but also the quality of the impedance is reversed because of the fact Z comes below. It is not k square into Z as it happens in a transformer. Therefore, this gyrator representation is like this, and you can write down the basic equations, and if some impedance is connected, what is the impedance seen by the input port can be easily calculated. Okay. Now, after, and also remember that gyrator is not symmetric. Anyway, transformer is a symmetric, and last time we discussed, if two gyrators are connected in series, that becomes cascade, it becomes an equivalent to a transformer. Anyway, now today what we will be doing, that is we will be studying now whether such a circuit, how to realize this kind of two port network or things like that. We will not go deep into that, but using some op-amp circuits, it can be realized. Such a relationship you can make it to happen by using some operational amplifiers. Now, today what I will be doing here is we will give you some idea of solving a circuit having some op-amp present in the circuit. Okay. So, circuit with op-amps called operational amplifiers. Simple circuits, and you will be able to solve no matter how the op-amps are connected with various resistances, things like that. But our discussion will be limited to the study of ideal op-amps only. I will consider, also indicate how to handle situations when the op-amp is not ideal, but in most of the cases ideal behavior of op-amp circuits, if you know, you will be able to face even if the operational amplifier is not an ideal one. Now, the question is what is an op-amp? Op-amp is actually an amplifier, as the name indicates. The question is, what does it amplify? There will be two input terminals of an op amp, can be considered to be input ports. Okay? And this voltage, if you apply V 1 here, is often called like this: two input points where input signals can be connected, and this is called inverting terminal, and this is non-inverting. Terminals. And to this it has got an input impedance connected to the source. Now, what an op amp is, actually it is called a differential amplifier. What it does is that if you connect a signal V 1 with respect to some common point V 1, and if you connect another signal V 2 with respect to the same common point, then what it does is that it will amplify this signal whatever is the voltage with respect to that ground. This point is also grounded, and this is the output voltage. So, output voltage will be proportional to the difference of the input signals multiplied by a gain of the op amp. Okay. Now, ideal op amp means the gain tends to very high, very large. This input impedance is also very large, and if there is an output impedance, that is very low. These are the qualities of the op amp. I will explain to you what do they all mean. Okay. So this is the op amp. If you, some people will draw like this, these are the output terminals. Okay. This is how it will be shown: input terminal, output terminal, and this is the output terminal. If you want to show it like this, output terminal is this one. And all voltages are measured with respect to the common ground. With respect to this, you apply a signal here, with respect to this, you apply a signal here, and so on. Okay. Achha. Now, I will just tell you a very popular chip, op amp chip is available with respect to 741. To understand what are these terminals, it is some 8 pins will be there, 8 connections you can make. One terminal is 1, 2, 3, and then 4, and here it will be 8, 7 and 6. It is this terminal 6 where output is collected, output. Okay. And you this pin, that is pin number 3, where you connect that this is the non-inverting terminal, 3 is non-inverting terminal, and 2 is inverting terminal. And apart from this, there is 2 terminals for connecting supply, that is here minus VDC, you connect, some battery connection is necessary for this chip to work, and 7 is plus VDC. Okay. And to the terminal 8 nothing is connected, 1 is for some other purpose, it is generally not connected. So, out of these 8 terminals, let us identify with this circuit what are these terminals are, because rest of the things are not difficult. Only thing, just to give you a feeling that how things work, what you require is a battery. Suppose 15 volt supply is necessary, 10 volt, 15 volt, this is suppose 15 volt, this is suppose 15 volt. Then what you do, this 15 volt minus you connect it here, and plus 15 volt you connect it there, and this point is the ground point. There is no ground point within the chip. With respect to this ground point is this what I am telling. With respect to this, I will measure the inverting terminal voltage where I will apply signal, non-inverting terminal voltage I will apply some signal, and output will be available from this terminal which is marked 6, but that signal also will be measured with respect to this ground. So, what is this ground? The external DC supply, whatever you will be connecting to the chip, the common point of that. So, here minus BTC is applied, minus 15 volt, here plus BTC is applied, and this is how this we identify these terminals. Okay. So, operational amplifier is nothing but a differential amplifier. It amplifies what? It amplifies the difference of these two signals, that is V 2 minus V 1. V 2 you apply with respect to the ground. Where is that ground? No point in this chip. Ground is with respect to you have created while giving supply to this op amp. We will not go deep into this, that is how it is realized with the help of transistor, this that. This is outside the scope of this one. But we would like to know, okay, this op amp circuit are so popular, whether after learning circuit theory can I quickly find out or analyze the circuits efficiently. That is what the goal will be. So, with this in mind, I will now discuss about this operational amplifier a little more. So it amplifies this signal, and this V naught is terminal 6, mind you. This V 1 negative inverting is terminal 2 and non-inverting terminal 3. Got the point? So, this is how things will go. Now, let us come here. suppose, and this op amp will be represented like this, not those all the pins you show, here only you show the supply connections plus VDC and minus VDC, those two batteries, and common point of those batteries is the ground, and here it is minus inverting terminal and plus, these are the 2 points, and here is your output pin 6, that also is not written while drawing the circuit, this is output voltage we call it, got the point. So, that is the thing, and ground point exists at the center of the battery, with respect to which I measured this voltage, I measured this voltage, I measured this voltage, that is the all thing. Now, suppose this voltage I call V 2 and this voltage I call V 1 with respect to this ground, and I want to sketch the output voltage V 0 as the difference of these two voltages V 2 minus V 1 against V 2 minus V 1, how this output voltage changes. Now, as I told you, this output voltage, there is a gain of this op amp and the value of this is A V 2 minus V 1. In the last page, I told you this is the output voltage, which is equal to A into V 2 minus V 1. This output characteristics will be very interesting if you sketch it. What is VDC? This one. This is the output voltage. Now, what is the gain? Gain I told you infinitely large. Okay, this relationship will hold good between these 2 points, and this curve will be steeper and steeper if the gain is higher and higher. Got the point? Minus VDC plus VDC. This zone, we will say if the op amp operates in this zone. So, V 2 minus V 1, if this value is outside this range and this range is very small because the gain is very high, and this relationship only holds good between these two range. Beyond this, what we say, op amp is saturated, saturation zone, saturation zone, and this portion is the linear zone. Clear? Maybe in a practical op amp, this may be spanning over some microvolt level, very steep. And for an ideal auto transfer op amp, it will be like this. It will be almost like a vertical line. Ideal op amp. This is plus VDC and this is minus VDC. This will be the thing, and here you are sketching V 2 minus V 1. that is a slight voltage difference V 2 minus V 1 will give you, and this is what we are sketching, output voltage. Your output voltage will be plus DC, and if it is less than that, this is 0, it will be minus VDC. So, op-amp ideal circuit, if you just use in this form, this circuit can be used as, for example, what I mean to say, suppose I have an op-amp circuit like this. This is your output, this is the thing. Suppose you make this point grounded, and here you have applied a voltage V, and suppose this applied voltage is sinusoidal voltage, what I am telling. That is the V 2 signal. What is V 1? V 1 is equal to 0, because with respect to ground all the potentials will be measured. So, this is V 2, this is mind you time. Then what I would expect at the output? The question is this. Suppose it is an ideal op-amp, a slight increase V 2 minus 0 volt into the gain, but that zone is very little. So, V 2 is greater than V 0 means it will immediately go to high plus VDC. VDC. VDC is of what? VDC of the op-amp. Two supply you will connect. It will saturate, because this voltage, a slight value of this voltage, maybe of the level of microvolt level here, this much voltage immediately saturates. For ideal transformer, this V 2 greater than 0, it saturates, it starts from here. And during this zone, V 1 is 0 and V 2 is negative, is not? Therefore, it will be negative excursion. So, this output voltage will be like this. Therefore, with this circuit, of course, you can convert a sinusoidal voltage to a square wave voltage, or you can, such a circuit is called comparator circuit. No feedback is used, comparator circuit, very much used comparator circuit. To get the idea of zero crossing of this signal, it could be any other signal, but whenever this will go positive, it will become like this, and if it goes negative, it will become saturated to negative value. That is the thing. What is this axis? Time. So, any difference in the voltage V 2 and V 1 will make the output either go to a plus VDC or minus VDC. So, in such operations, the op-amp will operate under saturated condition, and no point in trying to tell that VDC by this V 2 is your A. No, it is saturated. That relationship is only true A into V 2 minus V 1. This is only valid when the op-amp is not saturated, is not saturated. Clear? So, this is the thing. Now, this is one of the just no feedback, nothing is used and you have connected like that. However, you can make much more interesting circuit with the property of this op amp. For example, one like this. I will only tell you the concept of, say this I will write minus. Generally people draw like this. This is inverting terminal, this is plus terminal. Okay. And suppose you connect one, this is called negative feedback, this is output voltage, and op amp circuits will mostly operate on negative feedback circuits. Suppose I have connected one resistance R2 here and another resistance R1 here, R1 here, and this point I have grounded. This is what I have done. I have made a simple circuit like this. Now, here you see I have used a negative feedback. The output voltage is fed back to this point here. Now, in this case, this is not VDC, I will not expect, because it is negative feedback is there. If it is some finite voltage and the op amp is operating in the linear zone, now the op amp will operate on linear zone, meaning that the voltage required to get V naught here, how much will be this? This voltage will be V naught by A, that is what will exist, because differential amplifier. So, between these 2 points, whatever is the voltage, that gets amplified. So, this op amp will now operate in the linear zone with very high gain. So, if you get some finite output voltage, the input voltage required between these 2 points will be V naught by A, and A is very large. So, a little voltage here will cause a finite output voltage to appear in this circuit. So, to get V naught, the difference voltage required will be equal to V naught by A with A tends to infinity. For ideal op amp, it is infinity. Therefore, how much will be the voltage between these 2 points? Practically 0. Compared to whom? Compared to the finite voltage with which we are working. I will give some input signal here. For example, you give V1 here of the level of say millivolts. But this zone, as I told you, it is microvolt, less than that even, this linear zone. Therefore, the voltage existing between these 2 points compared to this V1 or V naught can be neglected. So, V naught by A will be much smaller than your input signal or output signal. Therefore, voltage difference will be practically not existing between these 2 points. And also the input impedance between these 2 points is very high. Therefore, no current will be drawn by the op amp. This side there will be practically no current. Yes, there will be current. How much that current will be? The small voltage V naught by A divided by this R naught. But what I am telling, R naught is very large and B naught by A is also a small number. Therefore, this current will be 0. So, when the op amps will be used in this sort of negative feedback, one conclusion is that potential difference between this point and this point will be 0. That is, potential of this point and this point can be considered to be same. And this potential is 0, therefore, this potential can be also assumed to be 0, and it is called then a virtual ground. Now, let me do one step, then you will understand and we will discuss it further. For example, I want to find out, analyze this circuit. So, I will say that look here, and let us assume it is an ideal op amp. So, this is the circuit, this is R2, this point I have grounded, and this is my output voltage, is not, and here I will connect my input signal V1. What is the consequence of this ideal op amp? Can it draw any current? No, input impedance is high, and for an infinite voltage you require very little voltage here compared to V1, which can be assumed to be 0. What is the point? In a circuit, if you are applying say 10 millivolt, and you are saying that in this circuit, this branch here is no current is flowing and voltage existing is very 0. Therefore, no current flows here. So, current here in this path is 0 straight, input impedance is higher, infinitely large, this fellow will never draw any current or very little current, which is of no consequence to the practical situation here. Now, this voltage is V1, clear. Therefore, what is the voltage here? 0 volt. So, this point, because voltage does not exist here. So, here also 0 volt, it is almost connected to the ground, no voltage drop here. So, write KCL at this point, say A, at point A. What will be the KCL? And also connect a resistance here. Oh, this I forgot to write, V1. Therefore, what will be the current in this path? This current will be V1 by R1. Why V1? V1 is with respect to this point, this is the potential, but this point is also here, because no drop takes place here. Potential difference between these 2 points is also 0. Therefore, V1 minus 0 volt here divided by R1 is what? Current coming in, and then current leaving. This current is 0, and this current will be how much? Going this way, we know from the circuit analysis, it will be V1 minus V naught by R2. KCL at this point A, V1 by R1, and the current in this branch, I am sorry, this will be how much? Potential difference between these two, it will be 0 minus this potential is 0 and this potential with respect to V naught, and current direction this way I am calculating. So, 0 minus V 0 plus R2, and these two should be same. Or you will get V naught is equal to minus R2 by R1 into V1, that is all. So, here nothing like saturated voltage will appear across the output. What you get in essence is an amplified version of the signal V1. If R2 is greater than R1, suppose R2 is 2 times R1, whatever is the input voltage, it will be twice appearing at the output with an inversion of sign. Anyway, we will continue our discussion in the next 2 lectures. Please be with me. Thank you.